I'm Anil Kumar sharing with you a very important concept of finding derivatives with first principle. The question here is, determine differentiability at x equals to 0. Explain using first principle. So let's try to understand the question. When I say differentiability at a point, we mean that the derivative of the function should exist at that point. In this case, that point is x equals to 0. So we say that if and only if f dash 0 exists. So we'll say f of x is differentiable at x equals to 0. Perfect. So that is the concept. Now, when we say first principle, what do we mean? Now, you found that rate of change when you worked with, the definition was that it was very popular equation, right? So we gave it a short form. So that rate of change, which is defined with limit h approaches 0, f of a plus h minus f of a over h, is utilized to find slope of a tangent line at a point a, x equals to a, right? At a point x equals to a. And since it is very popular, we have given it a name of derivative. So derivative is the same thing as finding instantaneous rate of change in a way. Okay, so that helps. So when we say using first principle, you have to use this equation. Correct? Now, since x is equal to a, basically we are trying to find at a point 0, limit h approaches 0, f of, so it becomes 0 plus h, right? So I'm writing 0 plus h just to remind you that a has been replaced with 0. Is it okay? Over h. This is what we're trying to find. And if it is a valid value, if this is equal to, let us say L, if this is equal to L, then we say it exists. So if L, so we say if and only if, right? So if it is a value L, a real number, then differentiable. So I hope the concept is clear. Now we are going to use this concept with different kinds of functions. These are all the functions. Square root x, square root of absolute value of x, square root of x squared, absolute value of x times x squared, and cube root of x. Now, from previous test papers I saw, one of these questions are always there in your test paper where you may go wrong. So it's kind of very important exercise to do. So you can actually pause the video here, solve this question, and check with my solution. So I'll do one by one for each function, correct, in this part. Now let us determine differentiability at x equals to 0 for the function f of x equals to square root x. I'm going to explain it using the first principle. Now when I say first principle, it really means that we could write derivative of a function as limit h approaching 0 for f of a plus h minus f of a over h. So that is at a point x equals to a, right? So this is at a point x equals to a. I should have written, let's say, f dash a here, right? That makes more sense. That's what we're trying to say. And to be very specific, our point a is 0 for the given example. So basically, we're trying to find the derivative at 0 for the given function, which is square root x. So I could write this as limit h approaching 0. Since it is square root of x, so a plus h, where a is 0, will be square root of, let me write 0 plus h here, minus square root of 0 over h. So I hope all that is clear, right? So basic definition is f dash x equals to f of a plus h at a point we're talking about, which is f dash a, since the point is at a. And if we are saying x is equal to 0, that means I could write 0 for x, right? So this is what you get. Limit h approaches 0, square root 0 plus h minus square root 0 over h. And clearly this is limit h approaches 0 of square root of h, that is 0, over h. Or we get limit h approaches 0 of 1 over square root h. Now since h is in the denominator, if I write 0 here, we get undefined. Right, so that is one way of showing it. You should also understand why it is not existing. The limit does not really exist. Let me show you with the help of the graph itself. The graph of the function square root x is kind of like this. This is square root x, right? So for any particular value of x, if the function f of x is square root x, the tangent at 0 is actually a vertical line, right? So that is the tangent. Now this tangent actually is only defined from when we say h is approaching 0 from the right side. Do you see that? Of this particular function square root of x, right? I should say from the right side it is undefined. You should notice that we cannot approach from the left side since it is a boundary condition. Is it okay? So strictly speaking, I should write this limit is undefined for h approaching 0 from the right side, and it does not exist for h approaching 0 from the left side. Do you see that? So I'm reluctant to really write down whether it exists or not, but in either case, what you say is that the function is not differentiable. And so the conclusion from here is, that f of x equals to square root of x is not differentiable, at x equals to 0. Perfect. X equals to 0 is in the domain of the function. However, it is not differentiable. Now, the question for you, I will write down a question for you, is what is the limit? I should say, what is the whether it is differentiable, what is the limit? What is the let me change the question. Is it differentiable for x greater than 0, right? So let this be the question for you, right? So I hope that makes sense. So with that, we have already seen that the function square root x is not differentiable at x equals to 0. Let us take the other functions. Now the second question for us is f of x equals to square root of absolute x. Now square root of absolute x is slightly different from square root of x. Here you see x belongs to all real numbers, is the domain. In the previous case, x was greater than or equal to 0. Now how will this function look like? Let's try to sketch and understand this function. So square root function will have something like this now. So both positive and negative values for x are permitted. So we'll have a function which will be kind of like this. So basically we have a combination. So we could write this as f of x equals to square root of a piecewise function, square root of x for x greater than or equal to 0 and square root of negative x for x less than 0. Do you get it? So that is going to be the function. Perfect. So there are two pieces to this particular function, and you can see if you approach from either side, we are approaching a vertical line, correct? So we are approaching a vertical line, and the process is going to be similar to what we did in the last example. However, you'll find two particular limits since we are approaching from two different sides, correct? So you can say f dash x is equal to limit h approaching 0 from negative side of f of let me write general function x plus h minus f of x over h, and then we'll also work on we are trying to figure out at x equals to 0. So I could have written like this also, f dash of 0. This time we'll work on the limit h approaches 0 from the right side, and the function will be f of 0 plus h minus f of 0 over h, right? So we have included x equals to 0 in our later expression, and you could actually write like this here also. Perfect. So if you do this, just as we did last time, what you get here is limit h approaches 0 from left side, and the function is, as you can see, square root of x. So what we get here, for 0, we get square root of 0 plus x, correct, minus square root of 0 over h, h. Okay, so that gives you limit h approaches 0 from the left side of square root of h over h, correct? And this is, undefined, right? Now, similarly, for this case, when you are approaching from the positive side, what do you get? So when you are approaching from the positive side, from the negative side, the function was minus x, but plus or minus, it doesn't really make a difference. So it becomes 0 itself. So what we get here is limit h approaches 0 from the positive side, the function square root of x now. So we'll have square root of 0 plus h minus 0, right, over, square root 0, right? So this also gives you square root of h over h, which is also undefined. So in this particular case, since it is undefined, we conclude that function is not differentiable, right? So we conclude that not differentiable. Perfect, because they are both undefined. Right? So I hope the steps are clear. Let's move on and take the other examples. Now let us try to determine differentiability at x equals to 0 for the function f of x equals to square root of x squared. We are going to use the first principle to show the differentiability. So using first principle, we can write that f dash 0 is equals to limit h approaches 0, f of 0 plus h minus f of 0 over h, right? Now in our case, the function is square root of x squared. Now what does that square root of x squared means? Let's try to understand that part also, and then we'll continue with our discussion. Let me show you here on the right side. So the function fx equals to square root of x squared is basically equal to, it is always positive, right? It is not x, because x could be negative. square root of x squared is absolute value of x. So you could write this function f of x as equal to x for x greater than equal to 0 and minus of x for x less than 0. Right? So it is basically an absolute function, right? So this is very important to understand. So now we could write this as f of x equals to absolute value of x. Perfect. So that will give you limit h approaches 0. So we get absolute value of 0 plus h, absolute value, minus absolute value of 0 divided by h, which is limit h approaches 0, absolute value of h over h. Now absolute value of h, if you approach from the left side, is negative, and if you approach from the right side, it is positive, right? So we could write this as limit of this function now is really equal to limit when h approaches 0 from the left side, so minus, is it okay? And also limit when h approaches 0 from the right side. Now if you approach from the left side, then what is the absolute value of h equals to? It is negative h, right? So you could write this as negative h over h. When you approach from the right side, it is positive h. Do you see that? Positive h over h. Now this could be written as, from both the sides, if you write, so this implies that the derivative, when you approach from the left side, is minus 1, right? H divided by this. This is when h is being approached from the left side, and is positive 1 when h is being approached from the right side. You get it? Now these two values are different, right? And therefore, since they are different, we say not differentiable. The reason being different values. So we can justify that since one side limit are not same, the function is not differentiable. Okay, so that is how I can show it. So this function is not differentiable at x equals to 0. Now if you sketch this function, it will look like this. Let me just, like an absolute function. And you can see for yourself that at x equals to 0, we are not sure what is going to be the tangent. Well, tangent could be minus 1 or it could be plus 1. So at 0, it is not defined, and therefore it is not differentiable at x equals to 0. Perfect. Now let's move on and take the next example. Now here we need to determine differentiability at x equals to 0 for the function f of x equals to absolute value of x times x squared. And we'll again use the first principle to prove. So let's rewrite the function as such. This time we'll write function first. Function is absolute value of x times x squared. Now as you know, absolute value of x is equal to plus x when x is greater than equal to 0, minus x for x less than 0. We could write this function as a piecewise function, correct? So I could write this as x times x squared for x greater than equal to 0 and minus of x times x squared for x less than 0, or the function can be written as cube root, right? Cube function, x cube when x is greater than equal to 0, but minus of x cube for x less than 0. So that becomes your function. Is that okay? So that is the first step. Now let us find the differentiability using the first principle. So as you have seen in so many examples, f dash 0 can now be written as the limit h approaches 0 for f of x plus h, which is 0 in this case, 0 plus h minus f of 0 over h. So what we observe here is that this could be written as a piecewise function, right? So we'll now write this function as a piecewise function, since the limits from left and right could be different. So we'll write this as limit h approaches 0 from, let us say, right side, since I took greater than equal to 0 first, taking positive value of x cubed, right? So we get the function is x cubed now, right? So in this case, the function is x cubed. Remember this part. So this is x cubed when we are talking about approaching from the right side, right? So it is 0 plus h whole cube minus 0, since 0 cube is 0 over h, and limit when h approaches 0 from the negative side, it is going to be negative of this, right? So it is negative of 0 plus h whole cube minus, I may write 0 cube, right, over h. Does it make sense to you? So that is how it is. So we see that both these limits are what? So what we get here is limit when h approaches 0 from the right side is h cube over h, and from the left side it is h approaches 0 is minus of h cube over h. So as you see, it is important to take one side limit for absolute functions, right? So now we could simplify and write this as the derivative of the function at 0 will be limit h approaches 0. When I say plus, it means from the right side. H cubed divided by h is h squared, right? And here we have limit h approaches 0 from negative side is minus of h squared. Correct. Now if I substitute 0 here, I get 0. Perfect. So what I get basically is that this limit is from either side, it is 0, right? So which is 0, right? When these two limits, side limits, are same, then we say that the function is differentiable, right? So now we can say the function is differentiable. Absolute value of x times x squared is differentiable. Right? So I hope the concepts are clear and you've seen how we can use the first principle to show whether the function is differentiable or not. This is the last example. We'll now consider differentiability of the function cube root of x at x equals to 0. So at times it is also good to sketch a function and then see the result. So if you sketch cube root of x, how will it look like? Why don't you pause the video, sketch it, and then look for yourself, right? So we want to sketch cube root of x. So the function will be on the right side, it will be kind of like this. And on left side of y-axis, it is going to be like this. Is that okay? Now, from this, what do you expect? Is it differentiable at x equals to 0 or not? Right? Think about it. And let's also do it using the first principle. Using first principle, we can write that if it is differentiable, then the derivative of f at 0 should exist, right? So this should exist. That is the whole idea, right? Now, its existence we check with the first principle, that is limit h approaches 0 of f of 0 plus h minus f of 0 over h, right? So that is the difference quotient rule. Now in our case, it is cube root of x. So what we get here is limit h approaches 0, cube root of 0 plus h, right? So it becomes cube root of, let me write 0 plus h now, minus cube root of 0 over h, okay? This could be written as limit h approaches 0 cube root of h over h, which is limit h approaches 0. So what is this? This is, you could write this as h to the power of 1 over 3 minus 1. Is it okay? Which is basically limit, you could write directly h approaches 0, h to the power of minus 2 over 3. I'm using these 3-4 steps as sometimes it is not very clear to students how do we get 1 over h to the power of 2 over 3, right? So we could write this as limit h approaches 0, 1 over, this is negative power, so 2 over 3. Is it okay? So ultimately what you get here is that this limit is equals to 1 over h to the power of 2 over 3. So when h approaches 0, so it is kind of 1 over 0, which is not defined. Correct? So that is what you get. Since it is not defined, we say function is not differentiable. Perfect. Now can you tell me what does it really means? We are saying that the limit is not defined, it is 1 over 0, infinitely large, right? That is what it means. You will see from the diagram that at 0, the slope of the line is like vertical. Do you see that? Vertical tangent. So it is an example where you have vertical tangent at x equals to 0, right? So if you have a vertical tangent, then the function is not differentiable, and this is an excellent example for the same. So I hope all the examples which we have taken are well understood. We began with these set of questions. We were checking differentiability at x equals to 0 using first principle for all these functions, right? So which ones of these were those which were differentiable, right? So just now we said this is not defined. This function was, as you know, kind of like this, correct? So it is not differentiable, right? Not differentiable. And in this particular case, we saw that the graph of the function was, let me just make the graph of this function. It is like cube function, right? So it is like this here and kind of like this, correct? So here, this function was differentiable. Is it okay? That was differentiable. Square root of x was like an absolute function. Let me now just show this, and which is not differentiable. And when we say square root of absolute x, then this function could have been sketched with cube root functions on either side, right? So kind of like this. And here, you know, it is a cusp, right? So it is not differentiable, right? If you draw a tangent line, it is infinitely large, right? So it is again a cusp, right? So here we have an example where it is not differentiable because in this case it is a corner. Here it is not differentiable because in this case it is a cusp, right? So it is not differentiable. And the example which is right on the top, why is that not differentiable? Let's try to figure this out. Now, if you sketch this function, it will look like what? It will look like this. Now in this function, we cannot approach from the left side, and therefore it is not differentiable at 0. You cannot approach from the left side. That's the whole thing. The limit from both sides should exist. Perfect. And this one was not differentiable because it is a vertical tangent. Perfect. So what you observe here is that functions are not differentiable you can also get from the graph as what? So different conditions which we saw is at the boundary, right? So when you are at the boundary, that is first case, right? In the second case, we saw it could be a cusp, and then we saw it could be a corner. or it could be a vertical tangent. Do you see that? So those could be the conditions for not being differentiable, even when the function is continuous. What we see here is that the function is continuous, right? The other reason, is other reasons are include what? When you have a whole or an asymptote, right? So discontinuity. Perfect. So if there is a discontinuity, function is not differentiable. But continuous functions are not differentiable if you have a cusp or a corner or a vertical tangent, or it's a boundary like you see at square root x. So with that, I hope all the concepts are absolutely clear. I purposely took examples with absolute functions since students find it difficult. And I think the cube root also will help them understand how a vertical tangent is not really a defined value. Perfect. So with that, we come to a close of this. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'll be great. Thanks for watching and all the best.